All right, guys, so follow along here as we go. Now, key things to getting these questions right. Identifying whether the question is asking for a vector quantity or a scalar quantity. That's the single largest stumbling block, okay, in getting these questions right or wrong. Okay, for number 1, part A, is it asking for a scalar quantity or a vector quantity? Scalar quantity. Distance is scalar. Direction does not matter for part A. Does it matter for part B? It does. Okay, you're solving A and B quite a bit differently there. Okay, and same thing for number 2. It gives you all these forward, backward, and then it asks, what's the average speed? Does forward, backward matter? Nope, not at all. Okay, so it's important to read the questions carefully, and that's of course why I highlighted those. Okay, so that you would look at them and know, oh, that's vector or that's scalar. All right, so for question number 1. Okay, give them a mark for their givens. Okay, in part 1, the car moved 2,500 meters north in 75 seconds, and in part 2, it went 18 meters per second south. Okay, for 55 seconds. So give them the mark for their givens there. Okay, the first calculation we need to have if we're going to find the total distance is we have to find the displacement or distance in part 2. We don't know it. All right. So what we do then is we set up. Okay, we take our v equals d over t and we solve for d by multiplying both sides by t. Okay, so that's the operation here. 18 meters per second times 55 seconds gives us 990 meters south. All right, so give them a mark if they did that calculation. They don't necessarily have to have the south on that number to get the mark. Preferably, but if they have 990, they obviously knew how to do it. Okay. All right, so that's our first thing. Now, can I find the total distance traveled since I know how far it went in part 1? Okay, what do I do with those two numbers? Add them together, regardless of their direction. Okay, so 2,500 plus 990, okay, should give us 3,490 meters. Another mark for that step. All right. For part B, it wants us to calculate the average velocity. Average velocity is displacement, which is a vector quantity over time. So I take those two displacements I had, 2,500 meters north and 990 meters south, and now direction matters. So 2,500 plus negative 990, or minus 990, whichever you did, okay, over the total time. So this stage here is worth a mark. Okay, if they showed that these were opposite direction, they added the times together, okay, it should come out to 1510 over 130, which, when you do that operation, ends up at 11.6 meters per second north. They must have the north on there to get it right. If they don't, it's not a velocity. It's a speed, even if the number's right. Okay? Everybody with me there? All right. Questions on that one? All right. So that one, guys, was out of 5. Number 2, okay, we got the 3 parts here. If I want to find his average speed, I need to know his total distance traveled and his total time while running. All right, so I've got to find those things for each of the parts. So if they have some givens written down, give them a mark. All right, in part 1, they give me the distance traveled and they give me the speed at which it is traveled at. However, they do not give me the time for part 1, and since I need total distance and total time, my first calculation is to calculate the time for part 1. So manipulate v equals d over t for t, t equals d over v, give them a mark for that manipulation, and give them a mark for 1.5 seconds. All right. In part 2, they already give me distance and time, so I don't need to do any calculating for number 2 or for part 2 because I already have everything I need there. Okay? And in part 3, same thing. They gave me the distance and the time, so I don't need to do any calculating there. All right? My next step then is to do my total distance over total time calculation. All right? Now, distance again is scalar. It does not matter now whether those 15, 10, and 11 or 15, 10, and 15 meter sections are forward or backward. So 15 plus 10 plus 15 is 40. Okay, over the total time, 1.5 plus 1.1 plus 1.6 is 4.2. So give them a mark for this step. Okay, and then give them a mark for the final answer, 9.52 meters per second. If they just left it at 9.5, that's also fine. Okay, so that one is out of 5 as well. So how important is it to know which quantities are scalar and vector? Is it pretty important? Okay, when you're reading a question, you've got to know. Okay, when you read something, you say velocity, you've got to know right away, okay, that's a vector quantity, direction matters. Okay, if it says speed, you got to know right away, scalar, direction doesn't matter. All right, so it's important to know which ones are which. All right, so give them a mark out of 10, let them see it, put it in the box, and then we'll get going here on reading graphs. Okay, so kinematics graphs. We're only essentially going to be dealing with 2 kinds of graphs in this unit. We're going to be dealing with position versus time graphs, and a position versus time graph tells us where an object is at various points in time. It can be used to calculate some other stuff, but that's what it shows. Okay? The other kind of graph we're going to look at are velocity versus time graphs. Okay? A velocity versus time graph tells us how fast an object is going at various points in time. All right, that's what it shows, but a few other things can also be calculated from it. What you're going to have to do, okay, what I'm going to ask you on quizzes and tests is to calculate some of the things that you can get from each type of graph. So it's going to be up to you to kind of pay attention here so you see how you can use each graph to get different things. Okay? All right, so we got to know, first off, what information can be read from those 2 types of graphs. Okay, like we said, that's going to be position versus time and velocity versus time. Okay, those are the 2 types of graphs we're going to be dealing with. Okay, understand that graphs and equations from kinematics show the same information, but they show it in different ways. For example, you saw yesterday that v equals d over t is essentially the slope of a line on a graph that has meters and seconds on it. Okay, because when we go, you know, here's point number 2 and here's point number 1, essentially what we're doing is dividing distance by time. All right, that's where we get all of these equations that we're going to use, okay, in this course from. We get them from the graphs that we're going to use. Okay, and that's what the last point is. Okay, learn the kinematics equations are derived from the graphs we're looking at. Questions so far? All right. So, position versus time graphs, okay? Like we said, they represent the location of a moving object over the course of time. They tell us where something is during its travel. Okay? Now, looking at this graph here, okay? This is telling me where the object is at various points in time. What is the object doing then between 0 and 1 second? Right. It's not moving. How can we tell that? Where was this object at time 0? Right. It was at 20 meters. At the same place. At the end of at time 1 second, it's still at position 20 meters. It hasn't moved. So anytime you see that the line is not changing, that means it's horizontal. The object isn't moving. Okay? Kind of common sense there. And that if the initial position and the final position are the same place, it obviously hasn't gone anywhere. Now, what's it doing here? Moving forward. Okay? Congratulations to Dom. He is the first person to never have answered with accelerating. Okay? Most people, admit, probably were thinking, well, it looks like it's speeding up there, right? Because the line was going up, and automatically we think means going faster. Doesn't. Not on this graph. On this graph means going away. All right? And in this case, it's going away at a constant speed, or at a constant velocity. How do I know its velocity is constant? Well, not that it doesn't stop. It does actually stop up here. Okay? But in the first second, so between 1 and 2 seconds, it went from 20 to 40 meters. How far is that? 20 meters. Okay? So in 1 second, it went 20 meters. And then in the next second, how far did it go? 20 meters. Does that mean every second it's going the same distance? Then that means in every second it's going the same speed. Okay, it's covering the same amount of distance every second. It's going at a constant speed. So when we see this kind of a shape, we know the object is essentially covering the same amount of area each consecutive second, going the same speed. All right, everybody with me there? All right, what's going on here? It's stationary. Okay. At the beginning, at time 3 seconds, it's at 60 meters. At time 4.5 seconds, still at 60 meters. It hasn't gone anywhere. All right, so it's been sitting still for a second and a half. What's it doing here? Going the other way. Right, it's going backwards. Okay, its velocity is negative. It's going in the other direction. Okay, because it goes from 60 meters to 20 meters. The only way to do that is to go back. All right. Everybody follow me there? All right. Now, in this graph, what is this object doing? In that graph, it's accelerating. All right. If you go faster, if you continue to go faster and faster and faster, do you cover more distance every second after the first? Yeah, you do. Okay? Not only because you're moving, but because you're also moving faster than you were before. And that's what this graph is showing. Okay? In the first second, okay, this thing only went maybe a meter or so. Okay? But in the next second, between time 1 and time 2, it went quite a bit further than that. All right? You guys follow me here? Okay? It didn't go very far in the first second, but in the second second, it went quite a bit farther. And in the third second, okay, it went even further than that. And in the fourth second, even further than that. Fifth second, even farther. Only way for it to continue covering more and more distance each second is to be going faster and faster and faster. All right? So anytime we see a curve on a graph like this, we know the object is accelerating. Okay? Now in this case, accelerating means going faster and faster. What if the graph, instead of having a curve like that, had a curve like this? Right, it's decelerating. It's slowing down. How do we know that? Well, if you look here in the first second, okay, it went pretty far. Okay, but as we keep going along, it actually travels less and less, and the line gets flatter and flatter and flatter. Okay, you guys with me there? I drew this kind of wrong here on this first one here. All right, in the first second here, okay, so here's time 1 second. In the first second, here's how far the object went. Okay, in the next second, okay, the object went only this far. Okay, and in the third second, it went only this far. Is it slowing down? It is. Okay, everybody with me on that one? All right. Okay, so just little things that we don't have to memorize, okay? We just have to kind of recognize and use some critical thinking skills, okay, when we look at a graph and go, okay, if the graph's doing this, what does that tell me is going on? All right. All right, so we've got a few kind of notes here on that. If the graph is parallel to the x-axis, so it's flat like it is here, okay, the object's position isn't changing, so it's standing still, okay? If it's a straight line that's not parallel, like this part, then it's moving at a constant speed. Okay, or constant velocity. In this case, forward. In this case, backwards. All right, slope calculation. So we talked about these the last couple of days. Okay, slope is calculated using rise over run. All right, so if this was point number 2 and this was point number 1, okay, this would be my slope calculation. d2 over d minus d1 over t2 minus t1. Okay, is that essentially for this kind of graph? Distance over time, right? Because this is in meters and this is in seconds, right? So my rise is meters minus meters, that's meters, okay, divided by time minus time, that's seconds. My slope comes out to meters per second, all right? So you don't have to memorize what the slope of this kind of graph is. You just have to look at the units. When you do a slope calculation, what units are you dividing? Okay, if you're dividing meters by second, you get meters per second. Right? If you're dividing kilograms by weeks, you get kilograms per week. Okay? That could be, you know, how much weight someone's losing, let's say, if they're on a diet. Okay? You would graph that. All right, so everyone recalls how to calculate slope, right? We don't have to spend too much time on rise over run. Okay, so what we have to remember here is, how do I figure out what my slope represents? Okay, well, you look at the units. Right? If we look at the units and we go this divided by this, we'll know what it is. Meters per second are the units for velocity. Okay. All right. So we got a position versus time graph here. Now, how far does the object go in part A? Okay, it starts at 0 meters, and at the end of section A, where is it? It's at 6 meters. All right, so how far did it go? 6 meters. Okay, now what was its displacement? Yeah, or positive 6 meters, yeah, okay? Because we got negatives on here. We don't know whether that's up, down, forward, or backward, but we got positive and negative, okay? So we would say the displacement here would be positive 6 meters, okay? The distance traveled would be 6 meters. All right. It does that, and in part A, it's traveling at a what? A constant speed, okay, or constant velocity, we'll say. Could I calculate what velocity it's traveling at in part A? Okay, I just figured out how far it went, 6 meters. How long did that take? 2 seconds. All right, so then I could go rise over run and calculate slope, which would be the same as going 6 over 2, which is the same as going distance over time, or displacement over time in this case. Okay, and we'll get 3 meters per second. Right? Everybody with me there? These are the kind of things that you're going to get asked to do. Okay, you'll get given a graph and asked to calculate things about sections of it, or maybe the trip as a whole. Okay, that's what we're going to look at with this example here. Okay, what's the object doing in part B? Phil, what's it doing in part B? It's not going anywhere. Okay, its position at the beginning of part B is 6 meters. At the end of part B, still at 6 meters. Okay, what speed is it traveling at? 0. Yeah, it's not traveling anywhere. Okay, its velocity is 0 meters per second. All right. What's going on in part C of this graph? Right. It's going the other way. It's going backwards. All right. Is it doing that at a constant speed or accelerating? Constant speed, because it's not curved, right? Okay. In each time interval, it travels the same amount as the second before, right? Unless its amount of displacement is changing each second, okay, then it's traveling at a constant speed. All right. What is the distance traveled in part C? Okay, so in part C, we start at positive 6 meters, and at the end of it, we're at negative 10 meters. Not negative 4. I started 6 above 0. I ended up 10 below 0. 16 meters. That's the distance traveled. What's the displacement? Negative 16, right? Okay, so you'll find if you do this section by section, the magnitude of distance and displacement are the same. The only difference will be that the displacement gets a vector on it. Malcolm. It would have 2 curves in it, because it would be, yeah, it'd be weird. Yeah. All right, in part D, again, we got a flat line, which means the object is stationary. It's not moving anywhere. Okay, in which one, E or F, is the object moving faster? F. Okay, F is not right. F is not quite as steep. Okay, if the steepness of the line represents how fast we're going, then the steeper the line, the faster we're going, right? We just said on the last slide that if I divide Okay, or find the slope of these lines, it gives me meters per second. So the steeper the line, the more meters per second I have, the faster I'm going. Okay, everybody follow me there? All right. Now, you might get a question that asks you to do something like this. It might say, what is the object's displacement between 0 and 10 seconds? Okay, so if a question asks you, what's the displacement between 0 and 10 seconds, the first thing you want to do is mark where the object is initially and finally. All right, we've got our final position and our initial position. Everybody okay with that? All right, displacement is how far and in what direction you end up from your starting position. Here's where they started. Here's where they ended. What's their displacement between 0 and 10 seconds? Phil? -10 meters. Okay, how did we figure that out? We went final position minus initial position. Okay, -10 minus 0 is -10. All right, everybody follow that. Once I know that, could I find out the average velocity of this object between 0 and 10 seconds? Okay, I just figured out the displacement of the object, and I was already told how long that took. So -10 meters divided by 10 seconds, what's my average velocity? -1 meters per second. All right, you guys following me here? Okay, a lot of this just comes back to using V equals d over t. This is what some of those 2- and 3-part questions we were doing when we were doing V equals d over t look like on a graph. All right, when we said, you know, the object goes this far forward in 10 seconds, then it goes this far backward in 4 seconds, they would have a graph that looks something like this. Okay, let's try something else here. Let's try, what's the object's displacement over the whole trip? All right, so let's do the same thing we just did. Here's my initial position. Here's my final position. What's my total displacement? 0. My final position and my initial position are the same place. All right, so even though it went up and down, it still didn't end up in any different position than where it started. Did it still travel? Okay, so now what if I asked you, what's the total distance traveled? It's obviously not 0. Okay, so how would I calculate how far this object went over the whole trip? Right, add all of the sections together, not the slopes, but all of the sections together. So in part A, it went 6 meters. In part B, 0 meters. Okay, in part C, we figured out that it went from +6 to -10, which was 16 meters. I'm not putting a negative on there because I'm being asked to calculate distance, which is scalar. Okay, in part D, 0 meters. In part E, goes from 10 to 4, so that's 6, and then this would be 4 more. All right, so my total distance traveled, 6 plus 16 is 22, plus 6 more is 28, plus 4 more, 32 meters. Okay, is any of this really mathematically difficult? No, but you have to look at a graph and kind of think critically about what is this graph showing me, what is happening on this graph. That's the tough part of physics, okay, is being able to look at something and say, what is that telling me? All right. Okay, once I have that, could I figure out the average speed over the whole trip? Sure, right, because speed, v, is distance divided by what? Time, and the time would be, what, about 17 seconds? Okay, so 32 over 17 is going to be about 0.48 or something. Sorry, not 0.48. It's going to be about 1.9 something. Okay, everybody with me there? Yes. Okay. All right. So those are the kind of things you could get asked about a position versus time graph. Okay, especially one that had, you know, several parts to it. Okay. All right. Sometimes you're going to get a graph that looks like this. Still a position versus time graph, but what is this object doing? It's accelerating. Okay? Some parts of the graph show it speeding up. Some parts of the graph show it slowing down. Some parts of the graph show it accelerating backwards. All right? Which part of this graph shows the object accelerating forwards? Yeah, part A, right here. Okay? This part of the graph is showing that the object's speed is becoming greater in a forward direction. All right? What part of the graph shows this thing slowing down? That's what a lot of people will say. And because it's going downwards, that's the thought, is that means it's slowing down. But on a position versus time graph, a stopped object looks like this, right? So what part of the graph shows the line getting flatter? Yeah, up here at B. Okay? In fact, what B is showing is the object slowing down, slowing down, slowing down, and then changing directions and accelerating back the other way. And then at the end of C, Ty, okay, at the end of C, yes, now this object is once again starting to slow down because we see the line getting flatter. All right? So it's traveling, it accelerates backwards and then slows down and comes to a stop again. Everybody with me on that? Okay. All right. Now, once in a while, a question might ask you to calculate the instantaneous velocity at a certain point. All right? Now, what that means is calculate how fast the object is going even though its velocity is changing over the course of time. Okay? And of course, that's what this graph is showing. So I might get a question that says, calculate how fast the object is going at point A. Point A is right here. All right? Now, unfortunately, that graph shows an object that's changing speed. Okay? I need to figure out how fast it's going at that instant in time. So I can't use v equals d over t, because that would give me the average speed between the start and point B up at the top, and that's not what I'm looking for. I'm looking for exactly how fast this object is going at point A. In order to do that, I've got to tell you the only thing I understood in calculus. You don't have to do any calculus, which is good because I wouldn't be able to teach it to you. Okay? The only thing I understood in calculus was this. A line to a mathematician, or sorry, a curve to a mathematician is actually an infinitely large number of infinitely small straight lines strung together at increasing angles. All right? So if you've ever looked at a low resolution picture on the internet, okay? What do you sometimes see in those pictures if they're really low resolution? You see the blocks, you see the pixels, okay? Because a computer can only make curves by setting little tiny squares next to each other. If the squares are really, really small, you don't notice them because they're beyond the resolution of your eyes, okay? Like an HD TV would do that, okay? You wouldn't see the pixels because there's way too many of them, okay, in the space that you can see. If it's low resolution, then you see the little squares, okay? And you see that a computer is cheating, okay? And that it's trying to make a curved line using a bunch of straight lines. All right? Everybody follow me there? So essentially what I have to do, if I want to find how fast the object is going at point A, is I have to find the slope of that tiny little line that exists at point A. Now, how are you going to find the slope of a line that's so small it's smaller than one grid on your graph? Right? How are you going to get 2 points on your line if it's smaller than the distance between 2 points on your graph? The answer is yeah, it'd be pretty tough. Okay? But we'll cheat. Okay? What we're going to do is we're going to make that line longer. All right? How many people have heard of a tangent before? Okay, taking math, heard of a tangent? A tangent is a line that touches a curve but doesn't cross it. So if I draw a line that's tangent to this curve, like this dotted line is, okay, I've essentially made a line that's parallel to the little tiny line that exists at point A. Okay, so I go like this. All right. I've now made the little tiny line that exists at point A long enough to calculate the slope. And slope on this graph is speed. Okay, so now can I do a slope calculation? Yeah. All right. What if they asked me to calculate the instantaneous velocity at point B? It would be 0, yes, because at point B we said the object is kind of turning around. Okay, how can I prove that mathematically? I can do what I just did and draw a tangent line that just touches B. Okay, that's the tangent to B, agreed? What's the slope of that line? 0, it's horizontal. Horizontal lines don't have any slope. Okay, everybody follow? You're not going to be asked to do that very often in Science 10. In fact, I probably won't ask you, except maybe on a worksheet, but not on a quiz or a test. Okay, it's just important that you recognize what a curved line means, okay, on a position versus time graph. Okay, questions on that one? Right. Now, the other kind of graph we're going to look at are velocity versus time graphs. Okay, velocity versus time graph is just like it sounds. It shows you the velocity of the object over the trip. Okay, now I've got two graphs here. One's a position versus time graph. One's a velocity versus time graph. Do they look a lot different? Right? One's got a line that's going upwards, okay, and the other's flat. So this is the position time graph. Okay, what is this object doing along this line? Okay, is it traveling the same distance every second? Every time interval it goes the same distance, right? That means it's traveling at a constant velocity or constant speed. Okay, is that what this graph is showing? Okay, this is now a velocity versus time graph, and it says that the velocity of the object is 265 meters per second the whole time. Its velocity doesn't change. Okay, how many people when they first looked at this said that object's not moving? Okay, that's probably what most of us thought when we first looked at that, right? Because it's flat. And we just finished talking about how a flat line means an object's not moving on a position versus time graph. On a velocity versus time graph, it means the velocity is not changing. That means traveling at a constant velocity. Okay, everybody with me there? All right. Now, what if on this graph, instead of this line, I had that? What's that object doing? It's accelerating. What's that going to look like on this graph? A straight line, right? Not a flat line, okay? But a straight line like this. Okay? That shows an object increasing its speed, agreed? On that velocity versus time graph, it's showing that the velocity of the object is increasing. Okay? In the same way that that's being shown by this curve on this graph. All right? Again, it's just a matter of looking at a graph and saying, okay, this is showing velocity, and it looks like velocity is getting bigger because this line is going upwards. Okay? It's not a matter of memorization. It's just a matter of what's on this axis and what's this line showing me. Okay? All right. So, yeah, so it shows either a constant or changing velocity. Okay, in a velocity time graph, okay, each point has the same, right, and the line is parallel to the axis. So that's what we were talking about here. All right, let's look at the next one here. So this is also a velocity versus time graph of a person running a race. What are they doing in the first part of the race? They're accelerating, right? It's showing that their speed goes from about 0 to 8 in a little under 5 seconds. All right, that's clearly an acceleration. Their speed changed. What's going on up here? Staying at the same speed. Okay? They're traveling at 8 meters per second. Maybe that's as fast as they can run. It's not very fast, but maybe that's as fast as they can run. Okay? Give you an idea. Okay? Usain Bolt can run at his top speed. It's around 17 or 18 meters per second. Okay? Now, he's a freak of nature, okay? But, yeah, he can run really fast. All right? The average person, when they're sprinting, probably runs between 10 and 12. Okay, the average person. All right, what is this person doing right here? They're stopping, right? They're slowing down and coming to a stop. How do I know that? Well, because eventually their velocity becomes what? 0, and that means they're stopped. Okay? Everybody all right with that? Now, what if this graph, instead of ending where it does there at time 14 seconds, what if it continued on and did this? Right. Nope, not going into the ground. They're running along the ground. Okay? But it would mean that they slowed down, and then started running backwards. Okay? Imagine if someone strung a big bungee cord across the finish line of the race. Okay? You run, you hit the bungee cord, and you start slowing down because the bungee cord slows you down and resists you. Eventually, you're going to get to the point where you cannot stretch the bungee cord anymore, and what will happen? You will get slung backwards the other way. Okay? And that's what this would be showing. Okay? Their velocity increasing in a negative direction. Okay? Believe it or not, guys, when you slow down by accelerating in a negative direction. All right? It never seems that way to us because we're North Americans and we go everywhere in cars. Okay? And when we hit the brakes, it doesn't seem like the brakes are accelerating us in a negative direction because you can never actually move in a negative direction as a result of slamming on the brakes. All right? But in actuality, when you slow down, you are accelerating in a negative direction. Okay? It's just that the force of friction on your brakes can't actually propel you in another direction. All right? But if you ran into a bungee cord, that's what would happen. When you throw something up in the air, that's what happens. Okay? When I throw this marker up in the air, which way is it accelerating the whole time it's in the air? Nope. If it accelerated up, it would go into orbit. Okay? Because if it was accelerating up, it would be going faster and faster up, wouldn't it? The only way for it to come back down is for it to be accelerating backwards, down. Right? As soon as it leaves my hand, and my hand's not exerting any force on it anymore, it's accelerating downward. That's why it slows down, comes to a brief stop, and then starts to actually move downwards. Okay? But the whole time, its acceleration is exactly the same. Negative 9.81 meters per second squared. That's the acceleration due to gravity on Earth. Okay? If you were to, not that you would do this, okay, but if you were to jump off of a roof, okay, in the first second of your fall, you would accelerate from 0 meters per second to 9.81. Okay? Yeah, pretty crazy. All right? Everybody follow. All right. That means if you fall for 2 seconds, you're moving really fast. Okay? When you hit the ground, you'd be moving. It would be like if Usain Bolt ran into a brick wall at the end of his race. Okay? It would hurt a lot. Yeah? And if you've ever fallen off the top of a ladder, you probably fell for like a half a second. Okay? And you can still get hurt pretty bad. All right? Yeah, so don't fall off of high things. Have you ever jumped off the 10-meter diving platform at the swimming pool? Okay? You know, you're going fast by the time you get to the bottom. And again, you only fall for about a second and a half, maybe 1.8 seconds when you fall 10 meters. All right? So you're only going, you know, maybe about 15 or 18 meters per second. All right. So, things to remember about velocity versus time graphs. Okay? Vertical value of any point is the instantaneous velocity. Essentially, it's saying you can read how fast the object's going directly off the graph. Okay? Now, the other thing we need to look at is that the area underneath our best fit line will tell us how far we've gone on this kind of a graph. So I'm just going to go back to this graph here. Okay? So I've got this straight horizontal line. It says I'm traveling at about 260 meters per second. All right? And it does that for 5 seconds. Everybody okay with that? So if I know how fast it's going, if I know v, okay, is 260 meters per second, and I know the time is 5 seconds, can I calculate d? What do you think? Sure it can, right? I can just go d equals v times t. Well, is that essentially finding the area of this rectangle. The base of my triangle is 5. The height of my triangle is 260. Did I just go base times height? Yes, I did. All right. Now, how do I know to do that? Well, here's how I know to do that. If a question gives me a velocity versus time graph and wants me to find distance or displacement, I need to look at the units. Okay? I've got meters per second here. You might want to pay attention to this. Okay? Meters per second here and seconds here. If I'm asked to find distance, what are the units for distance? Meters. All right. So I've got meters per second and I've got seconds on the x-axis. How can I get the seconds to cancel? What mathematical operation will make meters per second and seconds over 1 end up with only meters? Zach? No, I don't even need to know the amount of time. I'm just looking at just at units right now. How can I get rid of the seconds here? No. What if I multiply these two fractions together? Okay, meters times seconds and seconds times 1 ends up with meters seconds over seconds. What happens to the seconds? What am I left with? Meters. Okay, so if you ever need to find something using a graph, look at the units that are on each axis and figure out what mathematical operation you need to do. It's either going to be division or multiplication. It's never going to be addition or subtraction. Okay? Which one of those two operations will give you the units you're looking for? All right? We did that with these position versus time graphs too. Okay? When we were asked to find velocity, we went, okay, well, I've got meters here and seconds here. If I divide those two, I'll get meters per second, which are the units for velocity. Okay, on this graph here, if I'm asked to find displacement, I've got to multiply meters per second times seconds, and I'll get meters, because the seconds will cancel. Okay, that's where, again, that formula comes from. Okay, that's the area underneath the line of a velocity versus time graph. All right, what if, instead of this, it had this shape? Could I still do that? Could I still find the displacement of this object by finding the area underneath the line? Yeah, I can. How do I find the area of a triangle? Base times height divided by 2. All right. Why is that going to work? Because it's still this equation. Base times height divided by 2. This thing's speed increased from 100 to, what do we got here? 550. Okay, the halfway point of that would be the divided by 2. Would that be the average velocity of this thing over that whole trip? Right? Half the time it was going slower, half the time it was going faster. Base times height over 2 still ends up being this. It's just going to be d equals VAV times t. Okay, so area underneath the line here is always going to give you the distance or displacement of the object. Okay. I know it's a lot to absorb here right now, guys, but you're going to get lots of time to work on this. Okay, you're going to get to practice this often. All right, so this is one you're definitely going to want to remember. Okay, I almost always ask about that, and by almost always, I actually mean always. Okay, I will always, at some point, ask you to calculate the displacement of an object using a velocity versus time graph. Okay, I want to go over this graph together, and then I'm going to have you do a few of these on your own. Okay, so this is a position versus time graph. All right, I want to calculate the total displacement of this object. So this graph, this position time graph, shows me what? What does it show me? It shows me the position of the object at various points in time. So if I know where the object is at the beginning and I know where it is at the end, can I get its displacement? Yeah. Okay. So its position at the beginning is 0.2 meters. And its position at the end is 0.5 meters. What's its displacement? 0.3 meters. Okay, how did we figure that out? Displacement is final position minus initial position. Okay, meters minus meters is still meters. 0.5 minus 0.2 is 0.3 meters. Okay, everybody follow? All right, what's the total distance traveled? Okay, now Cam pointed this one out earlier. Okay, he said if you want to find the total distance traveled, you got to add all the parts together. Okay, because distance isn't vector, it's scalar. All right, how far does it go here? 0, it's flat. Okay, and in this part it goes from 0.2 to 1, so that's 0.8. Okay, and here it goes from 1 to 0.5, so that's 0.5. Well, that would seem to tell me that the total distance traveled would be 0.8 plus 0.5. Okay, does it matter that this is backwards? Not if I'm looking for distance, it doesn't. Okay, so 1.3 meters, 0.5 plus 0.8. All right, average velocity. Well, I just figured out part of average velocity. Okay, average velocity is displacement over time, and I just figured out the total, no, sorry, I figured out the total distance. And yeah, we figured out the total displacement here a second ago. Okay, so the total displacement is 0.3 meters. How long does this whole trip take? No, I think each one of these is 1, so I think it's actually 7 seconds. Okay, right, because here's 1, 3, yeah, 5, so that'll be 7 there. Yeah. Okay, so whole thing is over 7 seconds, right? So 0.3 over 7 should give us 0.04 meters per second. Okay, any of these calculations really difficult? Okay, but you got to be able to read the graph, right? Okay, and then the last thing, what's the speed of the object? Well, we just found the distance traveled, okay, 1.3 meters. How long did that take? 7 seconds. So, okay, the distance over the time gives me the speed, so that's 1.3 over 7, okay, and I get 0.19 meters per second. All right, everybody okay with this? All right, we're going to practice this here for the rest of class, and then tomorrow we're going to do a lab in the hallway with the little motorized carts we have.